So this is part 2 of chapter 5 of The Beginning of Infinity, the Reality of Abstractions. It might better be called an appendice because there's not much left for me to read of chapter 5, but there's a lot more to say to do with David Deutsch's views on the nature of mathematics. And the nature of mathematics is the title of chapter 10 of David's first book, The Fabric of Reality. And I find that there's a lot of crossover here in the material. There's a lot of new material in chapter 5 of The Beginning of Infinity, but there are certain themes that are touched upon in The Fabric of Reality that don't quite get a voice in The Beginning of Infinity. David recently gave a talk at his Dirac Prize Medal Award ceremony in which he articulated one of the most profound differences that David as a philosopher has with the mathematicians. David has some really unique views when it comes to the nature of mathematics, and it connects directly to the reality of abstractions and to his work, of course, on quantum computation. Now, I want to try and explain why, and I suppose in part this will be a personal reflection. Like many people, I was inculcated with some supernatural ideas as a child. You tend to learn about some aspects of religious mysticism, and you learn about fairy tales. Sometimes these are presented as facts. And this has the effect that when you begin to take on a more scientific, rational view of the world and a more reasoned approach to these matters, you tend to relinquish a whole bunch of this. Some people not only relinquish these beliefs in the supernatural, but they become actively hostile to the notion that anything is supernatural at all, or anything could possibly be supernatural. And I think that's quite right, but this impulse, this reasonable rejection of the supernatural, has a tendency to misfire. Now, Richard Dawkins in The Selfish Gene speaks about genetic misfiring. Some examples of genetic misfiring are things like the so-called altruism gene. So the altruism gene is supposed to be the gene that causes social animals like ourselves to help others. But sometimes this could misfire. If it's all about the gene propagating through the environment, then if there is an altruism gene, a gene that causes social animals to help one another, not all members of the species will possess the gene. And so therefore, if an altruistic member of the species decides to help, to be altruistic towards a member who isn't such an altruist, so if there is an altruism gene or something like this, this can perhaps misfire. It can misfire in human beings, let's say, as it could cause you to help someone who refuses to help anyone else. In other words, the altruism gene might in some situations actively work to cause itself to be removed from the gene pool by helping those who help no one. Altruism could be blind in that kind of way. Or the gene that causes the desire for sex, the whole purpose of which is to encourage reproduction of a species, or reproduction of genes in general. This could misfire because it's still, the desire for sex is still there even in the presence of contraception and even in homosexual members of the species. So the desire doesn't actually help reproduction in some cases. Memes, rather than genes, might do the same thing. So rejecting the supernatural might be a meme that we all become inculcated with, or that we all learn at some point after we give up on, let's say, God and become atheists, those of us who have become atheists. But a misfiring of that idea, a misfiring of the idea that one should reject supernatural explanations, could be reject all non-physical explanations, or reject all explanations cast in terms of things that include non-physical entities. That's a misfiring, because not all non-physical things are supernatural, and not everything in the universe is physical. In particular, the laws of physics are not physical. Numbers are not physical. Mathematics is not the study of physical things, but abstract things, and so on. All of these things are non-physical, parts of abstract reality. Abstractions have a reality, and this reality can have effects on the physical world, as we saw in chapter 5. Now, there is one kind of abstraction that is particularly interesting, and that is the abstract reality described by mathematics. Not all abstractions are mathematical, but the mathematical ones are the ones that often get the most attention. And there are misconceptions on both sides, and David has recently spoken publicly about what he calls the mathematician's misconception. And we'll come to this shortly, but essentially we have two groups of people once more. On the one side, we have people who think that mathematics is about abstract entities, and we reason about those entities using mathematical intuition. And this is somehow done in a kind of abstract space. And as such, what is able to be proved there is proved with certainty. And so mathematics can deliver us with rock-solid true proofs. Mathematical knowledge on this account is of an altogether different kind than other kinds of knowledge. Mathematical knowledge confers certain truth upon its conclusions on this view, or at least truth of a kind that is more reliable or more robust or foundational than other kinds of knowledge. So this is one side of the debate. It might be called Platonic idealism. The other side of the debate is that everything in reality is physical. There is only a physical reality and nothing else. We are just atoms moving through the void. On this account, mathematics is a kind of useful fiction. It happens to describe parts of this physical reality, but it cannot possibly have a reality apart from the material world. This is sometimes called physicalism or materialism. Either way, this is of course a form of reductionism. It's sometimes seen as the uber-rational way to be. It rejects everything except what science, supposedly, deems as real. Usually through observation, so it's also a kind of empiricism. So we have two quite rational doctrines here, it would seem, but yet they both seem to contradict each other. Brilliant mathematicians who believe in perfect mathematical ideals that they can have knowledge of through their mathematical intuition, and that leads them down the path of certain conclusions. And on the other hand, hard-nosed materialism of the scientific types that say only physical stuff exists. So if you're a person who likes reason, you seem a little bit stuck. Do you prefer brilliant mathematicians, or do you like hard-nosed physics types? So let me steal a famous line from David Deutsch here. If you regard these two positions as being deeply informative of your rational worldview, then, quote, then they seem a little bit to conflict with each other. But that does not prevent them from both being completely false. And they are. So David walks the line between these two positions. On the one hand, mathematics is indeed about perfect ideal forms, but that is not what mathematicians can actually discover. It's rather like the laws of physics. Now they exist, but what we have are explanations of the laws of physics, imperfect. Our knowledge of them is subject to change and improvement. And on the other hand, as Chapter 5 has argued at length, it cannot be the case that reality consists only of atoms. Collections of atoms arrange themselves into patterns that are more than the sum of their parts. That's an abstraction. The reason the domino falls or doesn't in Hofstadter's argument, go back to the last video for this one, is because the input is either prime or it isn't. It's nothing to do with the laws of motion acting on atoms in the void. The explanation was 641 is prime. It's got nothing to do with quantum theory or general relativity. Those are explanations of everything regardless, but cannot explain why in that situation. So David's recent talk called The Mathematician's Misconception, given at the Dirac Prize Award ceremony, was an explanation of how proof must be a physical process. Now this is an amazing insight, and it's very counterintuitive. It's even caused people to have strong emotional reactions, especially mathematicians. So what is the mathematician's misconception? Well, it's the denial that proof is physical. Now this claim arises from mathematical intuition. The claim that because mathematical objects are Platonic ideals, they're not made of atoms, so far this is true, that when we reason about them, and reasoning on this view is a non-physical process, that what we get is some kind of mathematically ideal knowledge. The problem here is the step reason about. When a mathematician reasons, what they are doing is thinking. They're using their brain. It's an activity of the mind. Now, as I've argued before, the mind is a kind of software, and it runs on the hardware that is the brain. Or if you don't like that, or want some other language, reasoning, even mathematical reasoning, is something that brains do. Now, brains are physical objects. They obey physical laws. There's no escaping this. And so the repertoire of possible computations is in one-to-one correspondence with those of a universal Turing machine. And a universal Turing machine is the foundation, the theoretical foundation underpinning what all really existing physical classical computers are. So the repertoire of all possible computations that a brain can do is in one-to-one correspondence with those of a universal Turing machine. There's nothing a universal Turing machine can do that a person cannot. And there's nothing a person can do that a universal Turing machine cannot. Now, the first part of that is easy to show. A universal Turing machine just has to be able to write, read, and erase symbols on a piece of paper. That's it. Now, a person can do that. A universal Turing machine just has to be able to write and read and erase symbols on a piece of paper and be able to move from one square to the next. That's it. Now, a person can do that. Therefore, a person is a universal Turing machine. Done. By the way, a person is more than just a universal Turing machine, but I don't need that for the argument here. Now, the other half of what I said is about whether or not there's anything a person can do that a universal Turing machine cannot do. Well, in terms of computation, a universal Turing machine is universal precisely because it can compute anything that's computable. Now, if a person can do something else in terms of thinking that a universal Turing machine cannot, this means that thing is a non-computable thing. But now here's the kicker. David Deutsch proved that given computers are physical objects and obey the laws of physics, then the repertoire of all the possible motions of a universal quantum computer must include the motions of any physical object. That is, a quantum computer can simulate the deepest laws we have, namely the laws of quantum theory, and all matter obeys those laws. That includes brains, and so whatever a brain can do, because it's just made of matter, so too can a universal quantum computer. And therefore, we have the other half of our requirement. There's nothing a human brain, or a mind, can possibly compute that a universal computer cannot. And what a universal computer can compute is all the things that are possibly computable. A mathematician's intuition cannot escape this. The intuition itself is a computation of a kind. A mental activity must be. It could be simulated by a computer. And what a quantum computer does, like everything else in the universe, is obey physical laws. And thus, if the laws of physics were different, what could be computed would be different. Now, proof. Proving something is what mathematicians do. They prove things about numbers, about abstract objects. When they complete a proof in their mind, it's their mind that has computed it. But the possible proof cannot be of anything the laws of physics prohibit. But the possible proof cannot be of anything that the laws of physics have prohibited being proved. So there are many statements, indeed the overwhelming majority of mathematical statements, that are not provable. This is where Gödel's incompleteness theorems come in. One of the incompleteness theorems say that there are statements that are true in mathematics, but which we cannot possibly prove. And there's a proof of that. That's Gödel's incompleteness theorem. But that is only the case because the laws of physics are such that what can be proved prohibits us from ever finding the proof of those things. Turing's version of this is that there are some statements that are not computable or decidable, but this is equivalent. So there's a difference between what's true and what's provable. That's the point of both Turing and Gödel's proofs. And by the way, you can have systems such as so-called sentential or propositional logic, and in these systems, the axioms allow you to prove everything that is true within that system. Gödel's incompleteness theorem is called the incompleteness theorem because if you have a richer system of logic, something like simple arithmetic, then you end up being able to generate true statements that cannot be proved true as such. And this is the case for the overwhelming majority of logical systems that you can create. Therefore, the overwhelming majority of mathematical claims you can make will not have proofs. You won't be able to decide whether they're true or false, or if they're true, you won't be able to have a proof that they're true. The relevance of all this for here and now is that mathematical objects, perfectly true statements, are things we only have access to through proof, which is a type of computation. But computation requires a computer. And computers are physical objects obeying the laws of physics, which mandate that we cannot ever hope to have error-free computation. Error is just a part of physical reality. Now, I should mention as an aside that David's great contribution here was a proof of the Turing principle, namely that there can be a physical object whose repertoire of possible motions contains the motions of all other objects. That's not exactly his words, but This is now called the Church-Turing-Deutsch principle, and David has said that really Ada Lovelace deserves credit for this also. So to labour the point, the claim from some mathematicians, and here I'm drawing directly on David's talk at his Dirac Prize award ceremony, seems to be that out there in abstract space, there is some other definition of proof, such that it's not physical. So this is the mathematician's claim. There is another way to prove stuff in abstract space that's not physics. But if some process that doesn't conform to that definition was a way of knowing about some necessary truth, that process wouldn't be a proof of that truth. The repertoire of integer functions that Turing machines and quantum computers are able to compute is the same. They just differ in speed. But we only know they differ in speed from quantum theory. And so when mathematicians attempt to say that they have an intuition that says that they can prove things that in such a way that they're able to get their error free, and it's not the method of proof is not in some way subservient to our knowledge of the laws of physics, they're wrong, because all proof, even intuitions, that all mental processes, including their own intuitions, arise from the activity of the brain computing stuff. And when you compute stuff, you're performing a physical process. That's all that can be happening according to David Deutsch's proof of how quantum computation works and the relationship between computation, which includes all intuitions, all mental activities, all possible methods of proof, the relationship between that and the laws of physics. The laws of physics constrain what computation is, and all mental activities, including all intuitions and all methods of proof, are physical. Okay, so now let's return directly to Chapter 5 of The Beginning of Infinity, The Reality of Abstractions, and let's take note of the concluding remarks and how they synthesize with what I've just been talking about, primarily drawn from David's talk about the mathematician's misconception. And David writes near the end of this chapter, "Beauty, right and wrong, primality, infinite sets, they all exist objectively, but not physically. What does that mean? Certainly they can affect you, as examples like Hofstadter show, but apparently not in the same sense that physical objects do. You cannot trip over one of them in the street. However, there is less to that distinction than our empiricism-biased common sense assumes. First of all, being affected by a physical object means that something about the physical object has caused a change via the laws of physics, or equivalently, that the laws of physics have caused a change via that object. But causation and the laws of physics are not themselves physical objects. They are abstractions, and our knowledge of them comes, just as for all other abstractions, from the fact that our best explanations invoke them. Progress depends on explanation, and therefore trying to conceive of the world as merely a sequence of events with unexplained regularities would entail giving up on progress. This argument that abstractions really exist does not tell us what they exist as. For instance, which of them are purely emergent aspects of others, and which exist independently of the others? I'll pause there. So it tells us that abstract entities have an independent existence, but we don't know what they are exactly. So when people ask, what is the real nature of numbers? Abstract though they are, it's very difficult to say anything more precise than that. They're not physical, but they do exist. And if someone then asks, well, where do they exist? Well, the answer is simple. They're not physical, so there is no where that applies to them. Where asks for a point in space, and space is something that's part of the physical universe. And so asking about a where for a number is rather like asking what happened before the beginning of time. Grammatically, the sentence might make sense, but logically, it refers to nothing. I'll continue. David writes, would the laws of morality be the same if the laws of physics were different? If they were such that knowledge could be obtained by blind obedience to authority, then scientists would have to avoid what we think of as the values of scientific inquiry in order to make progress. My guess is that morality is more autonomous than that, and so it makes sense to say that the laws of physics would be immoral. And, as I remarked in chapter 4, to imagine the laws of physics that would be more moral than the real ones. Now, if there's ever been, I'll pause there, this is me speaking, if there has ever been a more non-relativist conception of morality, I haven't read it. What David is saying there is that morality has an independent, or possibly his guess is that it has an independent existence aside from the laws of physics. So it doesn't matter what your laws of physics are. It doesn't matter if you are some kind of super alien that has a bird's eye view of the megaverse, of versions of the universe with different physical laws or different kinds of multiverses. Other universes with different physical laws that meant you would have to commit immoral acts in order to make progress would be immoral. That there is an independence to morality that stands apart from the laws of physics. Now, David's guess, and at least I'm sure this is David's guess, is that, at least I guess this is David's guess, is that the laws of physics that we do have are not immoral. That, in fact, in order to make progress in this universe, that you have to be a moral person, you have to act morally. That immorality, in fact, is the way in which we don't make progress. In fact, that must be the case because, for example, we need to be able to speak the truth, we need to be able to tell the truth in order to make progress. That reality is connected to truth in some way, and so our articulation of the truth is the thing that allows us to make progress and solve problems. So our laws of physics are definitely moral. We can see that. I'll continue with what David writes. The reach of ideas into the world of abstractions is a property of the knowledge that they contain, not of the brain in which they happen to be instantiated. A theory can have infinite reach, even if the person who originated it is unaware that it does. However, a person is an abstraction too. And there is a kind of infinite reach that is unique to people. The reach of the ability to understand explanations. And this ability is itself an instance of the wider phenomena of universality, to which I turn next. Now, I won't turn there next. I'm going to turn, in fact, to chapter 10 of The Fabric of Reality, because I'd like to stay with this theme of mathematics and the theme of the reality of abstractions, and really focus on that part of the reality of abstractions that, personally, I find most interesting, and a lot of people do as well, about abstract entities that are mathematical entities. What mathematics is about, how we can come to understand what mathematics is about, and how we can explain what mathematical entities are, and a little more on the nature of proof. So in The Fabric of Reality, chapter 10, page 222, at the very beginning of the chapter, David writes, now he's spoken about in The Fabric of Reality previously, before we get to chapter 10, obviously, quantum physics and evolution and knowledge. And so what he writes here is, the fabric of reality that I have been describing so far has been the fabric of physical reality. Yet I have also referred freely to entities that are nowhere to be found in the physical world, abstractions such as numbers and infinite sets of computer programs. Nor are the laws of physics themselves physical entities in the sense that rocks and planets are. So again, if you have bought The Beginning of Infinity, if you're a fan of The Beginning of Infinity, you can see there's a lot of supplementary material here that really helps with The Beginning of Infinity. So The Fabric of Reality, fantastic book, and everyone should get it. So I'm not going to read the whole chapter here. I'm going to skip forward to the parts that I find are relevant to chapter 5. The next part is, David asks the question, do abstract non-physical entities exist? Are they a part of the fabric of reality? I'm not interested here in issues of mere word usage. It is obvious that numbers, the laws of physics and so on, do exist in some senses and not in others. The substantive question is this: how are we to understand such entities? Which of them are merely convenient forms of words referring ultimately only to ordinary physical reality? Which are merely ephemeral features of our culture, which are arbitrary like the rules of a trivial game that we need only look up, and which, if any, can be explained only in a way that attributes an independent existence to them? Things of this last type must be part of the fabric of reality as defined in this book, because one would have to understand them in order to understand everything that is understood. Now the next part that I won't read is David speaking about what's called Dr. Johnson's criterion. And Dr. Johnson's criterion is whether or not an entity kicks back, and by kickback, that would mean reacts in such a way or behaves in such a way, or you're able to find out something such that it was unexpected, that's surprising. And this is why we regard numbers as being absolutely real, because merely by defining a few axioms, the axioms of arithmetic, you can then go on to discover amazing things that are completely unexpected. A very simple one is the distribution of prime numbers. It's completely unexpected. We don't know what it is. We don't know what the next prime number will be. We have to go out and search. So having defined these axioms, it then seems to reveal this reality of infinite complexity. And so therefore numbers are of a kind of abstract reality, according to that last question that David asked right there. He said, which, if any, can be explained only in a way that attributes an independent existence to them. So that would be numbers. They have an independent existence. The next highest prime number that we find, no one knows when we'll find that next prime number, and no one knows what it is. But can anyone doubt that it exists? And if it exists, in what sense does it exist? It just exists, not physically. It's not, and in fact, the biggest prime numbers, don't kind of have any physical meaning. They can't possibly label anything in physical reality because they're so large that they are, orders of magnitude bigger than all of the number of particles in the universe. And so David writes, thus, abstract mathematical entities we think we are familiar with can nevertheless surprise or disappoint us. They can pop up unexpectedly in new guises or disguises. They can be explicable and then later conform to new explanations. So they are complex and autonomous, and therefore, by Dr. Johnson's criterion, we must conclude that they are real, since we cannot understand them either as being part of ourselves or as being part of something else that we already understood, but we can understand them as independent entities. So we must conclude they are real independent entities. Nevertheless, abstract entities are intangible. They do not kick back physically in the sense that a stone does, so experiment and observation cannot possibly play quite the same role in mathematics as they do in science. In mathematics, proof plays that role. Dr. Johnson's stone kicked back by making his foot rebound. Prime numbers kick back when we prove something unexpected about them, especially if we can go on to explain it too. In the traditional view, the crucial difference between proof and experiment is that a proof makes no reference to the physical world. We can perform a proof in the privacy of our own minds, or we can perform a proof trapped inside a virtual reality generator, rendering the wrong physics. Provided that we follow the rules of mathematical inference, we should come up with the same answer as anyone else. And again, the prevailing view is that apart from the possibility of making blunders, when we have proved something, we know with absolute certainty that it is true. Mathematicians are rather proud of this absolute certainty, and scientists tend to be a little envious of it. For in science, there is no way of being certain of any proposition. However well one's theories explain existing observations, at any moment someone may make a new, inexplicable observation that casts doubt on the whole of the current explanatory structure. Worse, someone may reach a better understanding that explains not only all existing observations, but also why the previous explanations seem to work, but are nevertheless quite wrong. Galileo, for instance, found a new explanation of the age-old observation that the ground beneath our feet is at rest, an explanation that involved the ground actually moving. Virtual reality, which can make one environment seem to be another, underlines the fact that when observation is the ultimate arbiter between theories, there can never be any certainty that an existing explanation, however obvious, is even remotely true. But when proof is the arbiter, it is supposed there can be certainty. So I'll pause there. There we have David setting up the mathematician's misconception. For the first, so he set this up decades ago now. But I'll skip a bit, and David concludes after writing a little more. For the idea that mathematics yields certainties is a myth too. Since ancient times, the idea that mathematical knowledge has a privileged status has often been associated with the idea that some abstract entities, at least, are not merely part of the fabric of reality, but are even more real than the physical world. Pythagoras believed that regularities in nature are the expression of mathematical relationships between natural numbers. All things are number was the slogan. This was not meant quite literally, but Plato went further and effectively denied that the physical world is real at all. Now I'm skipping a bit, and David talks a little bit more about Plato, and he then writes on Plato, however, the problem he posed of how we can possibly have knowledge, let alone certainty of abstract entities, is real enough. And some elements of his proposed solution have been part of the prevailing theory of knowledge ever since. In particular, the core idea that mathematical knowledge and scientific knowledge come from different sources, and that the special source of mathematics confers absolute certainty upon it, is to this day accepted uncritically by virtually all mathematicians. Nowadays they call this source mathematical intuition, but it plays exactly the same role as Plato's memories of the realm of forms. There have been many bitter controversies about precisely which types of perfectly reliable knowledge our mathematical intuition can be expected to reveal. In other words, mathematicians agree that mathematical intuition is a source of absolute certainty, but they cannot agree about what mathematical intuition tells them. Obviously, this is a recipe for infinite, unresolved controversy. Inevitably, most such controversies have centred on the validity or otherwise of various methods of proof. One controversy concerned so-called imaginary numbers. Imaginary numbers are the square roots of negative numbers. New theorems about ordinary real numbers were proved by appealing at intermediate stages of a proof to the properties of imaginary numbers. For example, the first theorems about the distribution of prime numbers were proved in this way. But some mathematicians objected to imaginary numbers on the grounds that they were not real. Current terminology still reflects the old controversy, even though we now think that imaginary numbers are just as real numbers. I expect their school teachers had told them they were not allowed to take the square root of -1, and consequently they did not see why anyone else should be allowed to either. No doubt they called this uncharitable impulse mathematical intuition. But other mathematicians had different intuitions. They understood what the imaginary numbers were and how they fitted in with real numbers. Why, they thought, should one not define new abstract entities to have any properties one likes? Surely the only legitimate grounds for forbidding this would be that the required properties were logically inconsistent. Surely the only legitimate grounds for forbidding this would be that the required properties were logically inconsistent. That is essentially the modern consensus, which the mathematician John Horton Conway has robustly referred to as the mathematicians' liberation movement. Admittedly, no one had proved that the system of imaginary numbers was self-consistent, but then no one had proved that the ordinary arithmetic of the natural numbers was self-consistent either. Now I'm skipping a very substantial number of pages here. Maybe one day I'll go back and actually do the fabric of reality. In fact, that's the plan. I will do a series on the fabric of reality once I've finished the beginning of infinity. This will take many months. And so I've skipped forward a number of pages, and then David writes, thanks to Gödel, we now know there will never be a fixed method of determining whether a mathematical proposition is true, any more than there is a fixed way of determining whether a scientific theory is true. Nor will there ever be a fixed way of generating new mathematical knowledge. Therefore, progress in mathematics will always depend on the exercise of creativity. It will always be possible and necessary for mathematicians to invent new types of proof. They will validate them by new arguments and by new modes of explanation, depending upon their ever-improving understanding of the abstract entities involved. Gödel's own theorems were a case in point. To prove them, he had to invent a new method of proof. I said the method was based on the diagonal argument, but Gödel extended that argument in a new way. Nothing had ever been proved in this way before. No rules of inference laid down by someone who had never seen Gödel's method could possibly have been prescient enough to designate it as valid. Yet it is self-evidently valid. Where did this self-evidentness come from? It came from Gödel's understanding of the nature of proof. Gödel's proofs are as compelling as any in mathematics, but only if one first understands the explanation that accommodates them. So explanation does, after all, play the same paramount role in pure mathematics as it does in science. Explaining and understanding the world, the physical world, and the world of mathematical abstractions is in both cases the object of the exercise. Proof and observation are merely the means by which we check our explanations. I'll pause there. Isn't that amazing? All the way back in the Fabric of Reality, 1997, we're getting a portent, really, of what is to come with David's TED Talks, what is to come with David's next book, and what is to come with the vision and the worldview that he's gifted us with. It's here in its nascent form in the Fabric of Reality. In fact, more than nascent form. I mean, he's really articulating it clearly. There's so much here, of course, that it's easy to have missed it. And I admit that having read the Fabric of Reality for the first time when it was published in 1997, I didn't fully get the centrality of explanation in science. And I didn't get it until the beginning of infinity. So I'm skipping forward a little more, and this is still in chapter 10, skipping some more pages, and David writes, "It is often suggested that the brain, the human brain, may be a quantum computer, and that its intuitions, consciousness, and problem-solving abilities might depend on quantum computations. This could be so, but I know of no evidence and no convincing argument that it is so. My bet is that the brain, considered as a computer, is a classical one. But that issue is independent of Penrose's ideas." Let's pause there. So he's just written a section about Roger Penrose, who does have this theory that it could be the case that the brain is a quantum computer, or at least relies on some kind of quantum effects. And I think there's a number of scientists, including neuroscientists, that kind of hint that they think that this might be the case. But as David says, there's no real evidence for that, and there's this problem of what's known as decoherence. In particular, in order for us to have a quantum computer that works, we need to be able to have quantum systems. We need to be able to have entanglement. And entanglement, so far as we can tell at the moment, only works when temperatures are sufficiently low such that noise doesn't affect the system. And the kinds of technology that I've seen, the University of New South Wales here in Sydney, where I am, is working on this. The kind of temperatures they need is very, very close to absolute zero. I mean, they're operating at some of the coldest refrigeration on the planet in order to get these things to work. So until we have a new theory of how to build quantum computers, really the argument for the human brain being a quantum computer is unconvincing. But David continues to write, Penrose is not arguing that the brain is some sort of universal computer, differing from the universal quantum computer by having a larger repertoire of computations made possible by new post-quantum physics. He is arguing for a new physics that will not support computational universality, so that under his new theory, it will not be possible to construe some of the actions of the brain as computations at all. David writes, I must admit that I cannot conceive of such a theory. However, fundamental breakthroughs do tend to be hard to conceive of before they occur. Naturally, it is hard to judge Penrose's theory before he succeeds in formulating it fully. So that's a very generous reading of Roger Penrose. I'm going to skip forward a few more pages here, and David writes, Plato tells us that since we have access only to imperfect circles, say, we cannot thereby obtain any knowledge of perfect circles. But why not exactly? One might as well say that we cannot discover the laws of planetary motion because we do not have access to real planets, but only to images of planets. The Inquisition did say this, and as I have explained, they were wrong. One might as well say it is impossible to build accurate machine tools because the first one would have to be built with inaccurate machine tools. With the benefit of hindsight, we can see that this line of criticism depends on a very crude picture of how science works, something like inductivism, which is hardly surprising since Plato lived before anything that we would recognise as science. If, say, the only way of learning about circles from experience were to examine thousands of physical circles and then, from the accumulated data, to try to infer something about their abstract Euclidean counterparts, Plato would have a point. But if we form a hypothesis that real circles resemble the abstract ones in specified ways, and we happen to be right, then we may well learn something about the abstract circles by looking at real ones. In Euclidean geometry, one often uses diagrams to specify a geometrical pattern or its solution. There There is a possibility of error in such a method of description if the imperfections of circles in the diagram give a misleading impression. For example, if two circles seem to touch each other when they do not. But if one understands the relationship between real circles and imperfect circles, one can, with care, eliminate all such errors. If one does not understand that relationship, it is practically impossible to understand Euclidean geometry at all. The reliability of the knowledge of a perfect circle that one can gain from a diagram of a circle depends entirely on the accuracy of the hypothesis that the two resemble each other in relevant ways. Such a hypothesis, referring to a physical object, the diagram, amounts to a physical theory and can never be known with certainty, but that does not, as Plato would have it, preclude the possibility of learning about perfect circles from experience. It just precludes the possibility of certainty. That should not worry anyone who's looking for certainty, but for explanations. I'll pause there. So that's great. So how do we know about these mathematical entities? Well, because we have theories. We have theories that arise from our study of physically existing circles, let's say, and then we can prove things about those physically existing circles that relate to ideal Platonic forms in some way, and this is true of all mathematical Platonic ideals. So mathematics is about these abstract entities. We only have access to the physical versions thereof, but there is a relationship between, and we know what the relationship is because we conjecture explanations, between the perfect abstract entities and our physical reality. David continues, I'll skip a little, and he writes, "Let us re-examine another assumption of Plato's, the assumption that we do not have access to perfection in the physical world. He may be right that we shall not find perfect honour or justice, and he is certainly right that we shall not find the laws of physics or the set of all natural numbers, but we can find a perfect hand in bridge or the perfect move in a given chess position. That is to say, we can find physical objects or processes that perfectly possess the properties of the specified abstractions. We can learn chess just as well with a real chess set as we could with a perfect form of a chess set. The fact that a knight is chipped does not make the checkmate it delivers any less final. As it happens, a perfect Euclidean circle can be made available to our senses. Plato did not realise this because he did not know about virtual reality. It would not be difficult to program the virtual reality generators I envisaged back in a previous chapter, such that a user could experience perfect geometrical forms. I'm skipping a fair bit more. There's a lot of really good stuff here that yes, I'll have to return to at a later date, but I just want to get to this the mathematician's misconception and the relevant material about the reality of abstractions. And so it's almost, I'm reaching the punchline here. And so I'll read this. This is all the way up at page 246 of The Fabric of Reality. And David writes, "A conventional symbolic proof seems at first sight to have quite a different character from a hands-on virtual reality sort of proof. But we now see that they are related in the ways that computations are to physical experiments. Any physical experiment can be regarded as a computation, and any computation is a physical experiment. In both sorts of proof, physical entities, whether in virtual reality or not, are manipulated according to rules. In both cases, the physical entities represent the abstract entities of interest. And in both cases, the reliability of the proof depends on the truth of the theory that physical and abstract entities do indeed share the appropriate properties." So, pausing there, a mathematical proof is about abstract entities, but we use physical objects in order to represent those abstract entities. Now, David says, he writes, "We can also see from the above discussion that proof is a physical process. In fact, a proof is a type of computation. Proving a proposition means performing a computation which, if one has done it correctly, establishes that the proposition is true. When we use the word proof to denote an object, such as an ink on paper text, we mean that the object can be used as a program for recreating a computation of the appropriate kind. It follows that neither the theorems of mathematics, nor the process of mathematical proof, nor the experience of mathematical intuition confers any certainty. Nothing does. Our mathematical knowledge may, just like our scientific knowledge, be deep and broad. It may be subtle and wonderfully explanatory. It may be uncontroversially accepted, but it cannot be certain. No one can guarantee that a proof that was previously thought to be valid will not one day turn out to contain a profound misconception, made to seem natural by a previously unquestioned, self-evident assumption about either the physical world or about the abstract world, or about the way in which some physical and abstract entities are related. Skipping a little more. And I think that this is where, again, on a personal note, I really had that sense on reading this chapter for the first time of the ground falling out from underneath you, the sense of vertigo and falling that previously throughout school and high school and university, I really was inculcated with the idea that mathematics was this solid, unchanging domain of certainty. And then I think I read this. David wrote, "A very similar misclassification has been caused by the fundamental mistake that mathematicians since antiquity have been making about the very nature of their subject, namely, that mathematical knowledge is more certain than other forms of knowledge. Having made that mistake, no one has a choice but to classify proof theory as a part of mathematics. For a mathematical theorem could not be certain if the theory that justifies its method of proof were itself uncertain. But as we have just seen, proof theory is not a branch of mathematics. It is a science. Proofs are not abstract. There is no such thing as abstractly proving something, just that there is no such thing as abstractly calculating or abstractly computing something. One can, of course, define a class of abstract entities and call them proofs, but those proofs cannot verify mathematical statements because no one can see them. They cannot persuade anyone of the truth of a proposition any more than an abstract virtual reality generator that does not physically exist can persuade people that they are in a different environment, or an abstract computer can factorize a number for us. A mathematical theory of proofs would have no bearing on which mathematical truths can or cannot be proved in reality. Just as the theory of abstract computation has no bearing on what mathematicians or anyone else can or cannot calculate in reality, unless there is a separate, empirical reason for believing that the abstract computations in the theory represent real computations. Computations, including the special computations that qualify as proofs, are physical processes. Proof theory is about how to ensure that those processes correctly mimic the abstract entities they are intended to mimic. Gödel's theorems have been hailed as the first new theorems of pure logic for 2,000 years, but that is not so. Gödel's theorems are about what cannot be proved, and proof is a physical process. Nothing in proof theory is a matter of logic alone. The new way in which Gödel managed to prove general assertions about proofs depends on certain assumptions about which physical processes can or cannot represent an abstract fact in a way that an observer can detect and be convinced by. Gödel distilled such assumptions into his explicit and tacit rules of his results. His results were self-evidently justified, not because they were pure logic, but because mathematicians found the assumptions self-evident. Skipping more, and just getting to the part that I think I've quoted more from the Fabric of Reality than any other section, where David writes, "That mathematicians throughout the ages should have made various mistakes about matters of proof and certainty is only natural. The present discussion should lead us to expect that the current view will not last forever either. But the confidence with which mathematicians have blundered into these mistakes, and their inability to acknowledge even the possibility of error in these matters are, I think, connected with an ancient and widespread confusion between the methods of mathematics and its subject matter. Let me explain. Unlike the relationships between physical entities, relationships between abstract entities are independent of any contingent facts and of any laws of physics. They are determined absolutely and objectively by the autonomous properties of the abstract entities themselves. Mathematics, the study of these relationships and properties, is therefore the study of absolutely necessary truths." Now I'm just going to pause and repeat that sentence. Mathematics, the study of these relationships and properties, is the study of absolutely necessary truths. Mathematics is the study of absolutely necessary truths. Let me continue. In other words, the truths that mathematics studies are absolutely certain. But this does not mean that our knowledge of those necessary truths is itself certain, nor does it mean that the methods of mathematics confer necessary truth on their conclusions. After all, mathematics also studies falsehoods and paradoxes, and that does not mean that the conclusions of such a study are necessarily false or paradoxical. Next is my favourite line of the entire chapter, and certainly up there with one of my favourite lines out of both books. David writes, "Necessary truth is merely the subject matter of mathematics, not the reward we get for doing mathematics." I love that. That's brilliant, and I think I've quoted it 100 times before. Necessary truth is merely the subject matter of mathematics, not the reward we get for doing mathematics. The objective of mathematics is not, and cannot be, mathematical certainty. It is not even mathematical truth, certain or otherwise. It is, and must be, mathematical explanation. And so I'll just read the conclusion now of this chapter. I'm skipping a little more. And David writes, "There are physical objects such as fingers, computers and brains, whose behaviour can model that of certain abstract objects. In this way, the fabric of physical reality provides us with a window on the world of abstractions. It is a very narrow window and gives us only a limited range of perspectives. Some of the structures that we see out there, such as the natural numbers or the rules of inference of classical logic, seem to be important or fundamental to the abstract world, in the same way as deep laws of nature are fundamental to the physical world. But that could be a misleading appearance. For what we are really seeing is only that some abstract structures are fundamental to our understanding of abstractions. We have no reason to suppose that those structures are objectively significant in the abstract world. It is merely that some abstract entities are nearer and more easily visible from our window than others." Now, I'm just going to read also his terminology section that he has in the Fabric of Reality, as he does in the Beginning of Infinity. And so his terminology includes mathematics, which he defines as the study of absolutely necessary truths. So again, mathematics is a study of necessary truth, but it doesn't mean that what you are able to prove are necessary truths. It's just the study of them. And so what you get is fallible explanations of those necessary truths. He defines proof as, in the traditional way, a way of establishing the truth of mathematical propositions, or a sequence of statements starting with some premises and ending with a desired conclusion and satisfying certain rules of inference. Or better yet, a computation that models the properties of some abstract entity and whose outcome establishes that the abstract entity has a given property. Mathematical intuition he defines as, in the traditional sense, an ultimate, self-evident source of justification for mathematical reasoning. And actually, it's a set of theories, both conscious and unconscious, about the behaviour of certain physical objects whose behaviour models that of interesting abstract entities. And then he mentions what's called Hilbert's 10th problem. And Hilbert's 10th problem was whether or not we could establish once and for all the certitude of mathematical methods by finding a set of rules of inference sufficient for all valid proofs, and then proving those rules consistent by their own standards. And then Gödel's incompleteness theorem is a proof that Hilbert's 10th problem cannot be solved. For any set of rules of inference, there are valid proofs not designated as valid by those rules. So that's it. That's the Reality of Abstractions, Chapter 5, The Beginning of Infinity, with some material from Chapter 10 of The Fabric of Reality. Next, I move on to Chapter 6, Universality, but I hope you enjoyed that extended appendice, I guess, to Chapter 5. See you next time.